Budapest, October 1944. Inside a converted textile factory on the eastern bank of the Danube, 3 Hungarian petroleum engineers hunched over laboratory equipment that hadn't been calibrated in 2 years. Major István Kovács, formerly a refinery manager at the Almazfusito plant, watched the viscometer readings with growing confusion. The amber liquid in the glass cylinder refused to behave according to any specification he had memorized during his 18 years in the industry. His colleagues, Dr. András Molnár and technician Ferenc Szabó, exchanged glances that mixed exhaustion with something approaching disbelief. They had been testing captured British fuel samples for 6 hours straight, and every single measurement told them the same impossible story. The engineers believed they would find inferior quality, contamination, or some chemical weakness that explained why the German regime had assured them for years that enemy production was primitive and failing. Instead, they were staring at data that would shatter everything they thought they understood about the conflict unfolding across Europe. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you're watching from. It really helps support the channel. What these 3 men discovered in that cramped laboratory would not only explain years of mechanical failures across the Eastern Front, but would also reveal the staggering industrial gulf that made the outcome of the war inevitable long before the final year arrived. Major Kovács had returned to Budapest 3 months earlier, after 2 years attached to the 2nd Hungarian Army as a fuel logistics officer. He had witnessed firsthand the catastrophic losses near the Don River, where entire motorized columns ground to a halt not from enemy action, but from fuel that turned to sludge in the brutal cold of January 1943. He remembered Captain Peter Horváth, a tank commander from the 1st Armoured Division, describing how his Panzer IV had simply stopped responding during a withdrawal from Voronezh. The engine hadn't seized dramatically or exploded. It had merely coughed, sputtered, and died like an old man giving up on life. When the maintenance crews finally reached the abandoned vehicle days later, they found the fuel lines clogged with a waxy substance that looked like candle drippings. At the time, Horváth had blamed sabotage or Russian partisans tampering with fuel supplies. The official reports echoed this explanation. Kovács himself had written similar assessments, because the alternative was too disturbing to consider. The fuel came from German refineries, processed according to specifications developed by some of the finest chemical engineers in Europe. It couldn't simply be inadequate. There had to be another explanation. But now, in October 1944, with the Red Army pushing into Hungary itself and the German regime's promises of secret weapons ringing increasingly hollow, Major Kovács had been ordered to conduct a comprehensive analysis. The Hungarian government, reading the writing on the wall, wanted facts rather than propaganda. They needed to understand what had actually been happening to their mechanized forces for the past 3 years. Dr. Molnár adjusted his wire-rimmed spectacles and peered at the distillation curve chart he had just completed. The British fuel sample, captured from a damaged supply depot in Poland 3 weeks earlier, showed a remarkably consistent boiling point range. The hydrocarbon chains were uniform, indicating extensive refining and quality control. He pulled out a comparison sample, fuel that had been delivered to Hungarian units from German sources just 2 months prior, and ran the same test. The difference was stark. The German-supplied fuel showed a wide variance in boiling points, suggesting a mixture of different petroleum fractions that hadn't been properly separated. It was the kind of fuel you might produce if you were desperately trying to maximize output while lacking adequate refining capacity. Dr. Molnár had seen similar profiles in the 1920s, when Hungarian refineries were still using primitive fractional distillation towers. This wasn't the product of advanced German engineering. This was the output of an industry pushed far beyond its capabilities. Ferenc Szabó, the youngest of the 3 at 28 years old, was testing cold flow properties. He placed samples in a refrigeration unit set to -15 degrees Celsius, simulating conditions common on the Eastern Front during winter months. After 4 hours, he extracted both samples. The British fuel had thickened slightly but remained fluid, flowing easily when the container was tilted. The German-supplied fuel had transformed into a semi-solid mass that barely moved. Szabó pressed his finger against the surface, and felt it give way like cold butter. He said to the others, his voice quiet with the weight of understanding, that this explained everything from the Don River to the Crimean collapse. This explained why entire armored divisions became stationary targets. They hadn't been outfought. They had been outproduced by an enemy whose industrial capacity allowed them to maintain quality standards, even while manufacturing fuel in quantities that Hungary and Germany combined could never hope to match. Major Kovacs sat down heavily on a wooden stool. He had lost friends on the Eastern Front, good men who died because their vehicles failed at critical moments. He had written letters to widows explaining that their husbands had fallen in honorable combat when the truth was far more bitter. They had been abandoned by logistics, betrayed by fuel that couldn't perform the most basic function required of it. The three men worked through the night, compiling data that grew more damning with each test. The British fuel showed an octane rating of 87, suitable for high-compression engines that could generate maximum power. The German-supplied fuel measured 72 octane, forcing engines to run at reduced compression ratios to avoid destructive knocking. This meant that even identical engines produced significantly less power when running on German fuel. The sulfur content told another story. British fuel contained less than 0.1% sulfur, indicating extensive desulfurization processing. The German samples ranged from 0.3 to 0.7% sulfur, a level that would cause accelerated engine wear and corrosion of fuel system components. Dr. Molnar calculated that engines running continuously on such fuel would require major overhauls 3 times more frequently than those using properly refined petroleum products. But the most revealing test came when they analyzed the aromatic content. Aromatics were hydrocarbon compounds that affected both octane rating and combustion characteristics. The British fuel showed a carefully balanced aromatic content of approximately 25%, optimized for consistent engine performance. The German samples varied wildly, from 15 to 45%, suggesting they were blending whatever petroleum fractions they could produce without regard for final performance. Ferenc Szabó found himself thinking about a conversation he had overheard the previous summer. 2 German technical advisors visiting the Budapest refinery complex had been discussing production quotas. One had mentioned that synthetic fuel plants in Germany were now contributing more than 40% of total production, using coal liquefaction processes that were energy-intensive and expensive. The other had responded that quality standards had been, quote, adjusted for wartime necessity, end quote. At the time, Szabó had assumed this meant minor compromises. Now he understood it meant something far more significant. As dawn broke over Budapest on the second day of testing, Major Kovacs drafted his preliminary report. He wrote with the precision of an engineer, but couldn't keep the emotion from his final paragraphs. The fuel disparity wasn't a minor technical issue. It represented a fundamental difference in industrial capability. The British, and by extension the Americans, could produce millions of tons of high-quality fuel while simultaneously maintaining strict quality standards. They had the refining capacity, the technical expertise, and the raw materials to ensure every liter of fuel met specifications. Germany, despite its vaunted industrial reputation, was running refineries at maximum capacity with inadequate feedstock, producing fuel that was barely adequate in summer conditions and dangerously inadequate in winter. The regime had prioritized quantity over quality, believing that sheer volume could compensate for inferior performance. But in mechanical systems, especially the complex engines of modern armored vehicles, quality wasn't negotiable. An engine designed to run on 87-octane fuel would never perform reliably on 72-octane, no matter how much of it you had. Dr. Molnar added a technical appendix that included detailed chemical analyses. He noted that the British fuel samples showed traces of additives designed to improve cold weather performance and prevent gum formation during storage. These were sophisticated chemical enhancements that required advanced organic chemistry capabilities. The German-supplied fuel showed no such additives and, in fact, contained contaminants that would accelerate degradation over time. The report was submitted to the Hungarian Ministry of Defense on October 28, 1944. Major Kovacs included a recommendation that Hungary immediately seek to negotiate a separate peace, as continuing the war alongside Germany was logistically untenable. He noted that if fuel quality was this poor, other critical materials were likely similarly compromised. An army couldn't fight effectively when its logistics infrastructure was fundamentally inadequate. The report was filed and apparently forgotten as events overtook Hungary. Soviet forces reached Budapest in December and the government collapsed. But Major Kovács had made copies, and one of these eventually reached Allied intelligence officers in early 1945. Captain James Morrison, a petroleum engineer from Texas, serving with the American Technical Intelligence Unit, read the Hungarian report with fascination. He had spent 2 years analyzing captured German fuel and lubricants, and Kovács's findings matched his own conclusions perfectly. Morrison had been puzzled by the poor quality of German petroleum products, given the country's reputation for precision engineering. The Hungarian report provided the missing context. It wasn't that German engineers didn't know how to make good fuel. It was that they lacked the industrial capacity to produce it in the quantities required by modern mechanized warfare. Morrison added his own analysis to the file. American fuel production in 1944 had exceeded 170 billion gallons, virtually all of it meeting or exceeding military specifications. German production, including synthetic fuel from coal, had reached approximately 15 billion gallons, with quality that varied dramatically depending on source. The British, despite being a much smaller country, had maintained production of approximately 8 billion gallons of consistently high-quality fuel through a combination of domestic refining and imports from the Middle East and Caribbean. The numbers told the story more eloquently than any propaganda. The Allied powers could equip their mechanized forces with reliable, high-performance fuel while simultaneously supplying their civilian economies. Germany was struggling to produce barely adequate fuel in quantities that left its military chronically short of supplies. Every German tank commander on the Eastern Front had learned to treat fuel as precious as ammunition because it effectively was. You couldn't fight if you couldn't move, and you couldn't move if your fuel turned to wax at the first sign of cold weather. But the human element of the story went deeper than statistics. In early 1945, after Budapest fell to Soviet forces, Major Kovács was detained by Red Army intelligence officers who were systematically interrogating anyone with technical expertise. He expected imprisonment or worse, but instead found himself in conversation with a Soviet engineer named Colonel Vladimir Petrov, who had read his fuel analysis report with great interest. Petrov, it turned out, had his own experiences with fuel quality issues. The Soviet Union had received substantial quantities of fuel from the Americans through the Lend-Lease program, and the difference in performance had been immediately obvious to Soviet tank crews. Vehicles running on American fuel could operate reliably in conditions that left domestic Soviet fuel frozen in the tanks. Petrov mentioned that the Ilyushin Il-2 ground attack aircraft, which required high-octane aviation fuel, had initially suffered terrible engine failure rates until American supplies became available in 1943. The colonel said to Kovács, with something approaching respect, that the major had identified one of the critical factors that determined the war's outcome. Industrial capacity wasn't just about producing more tanks or aircraft. It was about producing everything required to keep those machines operational under combat conditions. Fuel, lubricants, spare parts, ammunition, all had to meet quality standards, or the entire system collapsed. Kovács spent 8 months in Soviet custody, mostly answering technical questions about Hungarian and German petroleum refining capabilities. He was released in late 1945 and returned to Budapest to find the city in ruins. The refinery where he had worked before the war had been heavily damaged in the fighting, but he still had his engineering knowledge, and post-war Hungary desperately needed people who understood industrial processes. Dr. Molnar had been less fortunate. He had remained in Budapest during the siege and died when a Soviet artillery shell struck the apartment building where he was sheltering. His wife survived and kept his laboratory notebooks, including detailed records of the fuel analysis from October 1944. These eventually made their way to Hungarian technical archives, where they remained mostly forgotten until the 1980s, when petroleum historians began studying the logistics of the Second World War. Ferenc Szabo, the young technician, survived the war and immigrated to Canada in 1948. He found work with Imperial Oil in Alberta and had a successful career as a refinery engineer. In a 1983 interview for an oral history project, he recalled the October night in Budapest when he first tested the cold flow properties of British fuel. He said that moment was when he truly understood that the war was lost, not because of tactics or strategy, but because one side could produce quality fuel in unlimited quantities, while the other side couldn't maintain basic standards, even with drastically reduced output. The broader implications of the Hungarian fuel analysis became clearer as post-war researchers gained access to German industrial records. The German synthetic fuel program, based on Fischer-Tropsch coal liquefaction and similar processes, had been a massive investment that never came close to meeting requirements. The plants were expensive to build, energy-intensive to operate, and produced fuel that required extensive additional processing to meet military specifications. By late 1944, the synthetic fuel program was consuming resources desperately needed elsewhere while failing to solve the fundamental supply problem. Meanwhile, Allied fuel production had benefited from access to the richest petroleum deposits in the world. American oil fields in Texas, Oklahoma, and California were producing at rates that exceeded total European output. Middle Eastern supplies were flowing to British refineries. Venezuelan crude was supplementing American production. The refining infrastructure had been modernized throughout the 1930s, incorporating catalytic cracking and other advanced processes that maximized gasoline yield while maintaining quality. The result was a logistical mismatch so profound that it affected every aspect of military operations. Allied mechanized units could maneuver freely, knowing that fuel supplies were essentially unlimited. German and Hungarian units had to carefully ration every liter, which restricted tactical options and made sustained operations impossible. A German tank commander might have the best tactical training in the world, but if his fuel turned to sludge overnight, that training was worthless. Captain Peter Horváth, the tank officer whose Panzer IV had failed near Voronezh, survived the war and eventually learned about the fuel quality issues from a conversation with Kovács in 1946. The two men met by chance at a Budapest railway station, both trying to rebuild their lives in a shattered country. Horváth had spent 2 years in Soviet prisoner of war camps and looked 20 years older than his actual age of 34. When Kovács explained what the laboratory tests had revealed, Horváth was silent for a long moment. Then he said that he had lost half his company in the withdrawal from Voronezh, and most of those losses had come from vehicles that simply stopped working. He had written in his after-action report that the mechanical failures were unprecedented, but his superiors had dismissed the concerns as excuse-making. Nobody wanted to believe that German engineering could be at fault. Horváth mentioned that one of his sergeants, a veteran mechanic named Klaus Weber, had repeatedly complained about the quality of fuel they were receiving in late 1942 and early 1943. Weber had said it smelled wrong, looked cloudy, and left excessive residue in the fuel filters. The sergeant had been told to stop complaining and make the equipment work, because official specifications said the fuel was adequate. Weber had died when his disabled tank was overrun by Soviet infantry, unable to move because the engine had quit 3 hours into a winter march. The conversation between Kovács and Horváth lasted 2 hours, two men trying to make sense of a catastrophe that had consumed their youth and claimed the lives of their friends. They concluded that the fuel issue was emblematic of a broader failure. The German regime had built a military machine that required industrial support it couldn't provide. The initial successes of 1939 through 1941 had been achieved with equipment built up over years of preparation. But once those stockpiles were exhausted, the underlying weakness of the industrial base became impossible to hide. By 1944, German forces were using fuel so poor that it would have been rejected by any civilian refinery in peacetime. They were lubricating engines with substitutes that caused accelerated wear. They were replacing broken components with parts made from inferior materials because proper alloy steels weren't available. The entire logistics system was running on desperation and improvisation, and it showed in the steadily declining operational readiness rates of mechanized units. The Hungarian fuel analysis of October 1944 captured this reality in precise technical language. The three engineers had set out to understand a specific problem, why tanks and vehicles kept failing, and had uncovered a fundamental truth about industrial warfare. In a mechanized conflict, the side with superior refining capacity had an advantage as significant as numerical superiority in troops or equipment. Fuel quality determined whether machines could operate reliably, and reliability determined whether armies could execute their strategies. Major Kovács eventually resumed his career in petroleum engineering, working on reconstruction of Hungarian refining capacity during the 1950s and 60s. He rarely spoke about the war but kept a copy of his October 1944 report in his personal files. When petroleum engineering students occasionally asked him about his wartime experiences, he would show them the chemical analysis data and explain how quality control in refining was not just a technical nicety, but a strategic necessity. The lessons from the Hungarian fuel analysis were absorbed by post-war military planners, particularly in the United States. The Korean conflict saw American forces operating with fuel that met even higher standards than the World War II-era products, incorporating improved additives and tighter specifications. The Cold War competition between East and West included substantial investments in refining capacity, because both sides understood that future mechanized warfare would be won or lost in the refineries, as much as on the battlefield. The story of three Hungarian engineers discovering the truth about fuel quality in a makeshift laboratory resonates because it illustrates how technical details can have strategic consequences. Major Kovács, Dr. Molnar, and Ferenc Szabó weren't generals or politicians. They were engineers doing careful analytical work, measuring viscosity and octane ratings and cold flow properties. But their conclusions helped explain why entire armies had failed, why thousands of men had died, and why the outcome of the greatest conflict in human history had been determined as much by industrial capacity as by courage or tactics. The British fuel that so impressed the Hungarian engineers in October 1944 wasn't remarkable because it used exotic chemistry or revolutionary additives. It was remarkable because it consistently met specifications every batch, every delivery, month after month, year after year. That consistency was the product of industrial systems that had adequate capacity, trained personnel, quality raw materials, and the time to do the job properly. It was the mundane triumph of logistics over ideology, of engineering over propaganda, of industrial reality over wishful thinking. When Ferenc Szabó looked at that cold flow test in Budapest and saw British fuel remain fluid, while German fuel turned to wax, he was witnessing the physical manifestation of industrial capability. One side could maintain quality standards even while producing fuel in staggering quantities. The other side couldn't maintain standards even with drastically reduced output. That difference, multiplied across millions of tons of fuel and thousands of military vehicles, determined which armies could move and fight effectively and which would slowly grind to a halt. The German tanks didn't always stall because of poor tactics or inferior design. They stalled because the industrial base supporting them couldn't produce fuel that met the requirements of modern engines. The Hungarian engineers discovered this truth too late to change anything. But their meticulous documentation preserved a critical lesson about the relationship between industrial capacity and military power. In mechanized warfare, the refinery was as important as the factory producing tanks, and quality control was as vital as tactical doctrine. Major István Kovács died in 1978 at the age of 71. His obituary in the Hungarian Engineering Journal mentioned his contributions to post-war refinery development, but said nothing about his wartime analysis. The full story of what he and his colleagues discovered in October 1944 remained obscure until researchers in the 1990s began studying the technical aspects of World War II logistics. Their work revealed that the fuel quality gap was even larger than Kovács had documented, and that it had affected operations from North Africa to the Eastern Front. The final irony was that German engineers knew how to produce high-quality fuel. The technical knowledge existed. What didn't exist was the industrial capacity to implement that knowledge at the scale required by total war. The regime had gambled that superior tactics and equipment quality would compensate for industrial limitations. The Hungarian engineers proved that gamble had failed, not through any fault of German engineering skill, but because no amount of skill could overcome inadequate resources and insufficient refining capacity. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II and check out the video on screen for another incredible tale from history. Until next time.